of Chapter 2 will be on the chemistry of life. It will be on atoms. It will be on the nature of atoms, how atoms are constructed, and how atoms form bonds, and water. In the second video, we'll go over basically sort of the second half of Chapter 2, which will discuss organic molecules. So let's talk about the chemistry of life, and in this we're going to talk about the very basics of chemistry. And if you remember from when we talked about science in general, in order to understand biology truly, you have to understand some physics and some chemistry, because that's what biological organisms are made of. So I always like to tie things to the universe itself, because to me, looking up at the stars at night reminds me of the fact that we're all part of this universe. The atoms that make us up all come from the same material. So what is the composition of the universe? The universe is consistent of matter and energy. Matter is anything that takes up space, that's its technical definition, and energy is something which causes motion in matter. Everything is made of these two substances, with the exception of dark matter and dark energy, which are things we do not know much about yet, which those actually make up the majority of the universe. But everything that we know about, everything we can interact with, everything you can see, everything you can touch, everything you can do is matter or energy. And these two things are essentially the same thing. They're just in different states, is what it comes down to. That's what Einstein's theory, which is his equation, E equals mc squared, states is that you can transfer matter into energy, and energy can become matter, and they're both the same thing, just in different states. In this picture to the right, you'll see the Andromeda Galaxy. It's a neat structure. On a clear night, you can see it. It's very faint and it's fuzzy, and it's bigger than the moon. But it's another galaxy, and it's made of matter. And the light that we see from it is the energy transmitted from it. We see it was about a couple million years ago, because that's how far away it is from us. It's a couple million light years away from us. But we see it as it was a couple million years ago, and eventually we're in a collision course with it. Our galaxy is going to run into the Andromeda Galaxy. I wish I'd be around for that, but that's a couple billion years down the line. So the matter which can be seen is made up of one or more of what we call elements. And the element there used to be 4 elements. It used to be fire, earth, wind, and water. And the reason why is those are all the things that we could see or touch or experience without equipment that we eventually invented. And so we thought everything was made of earth, wind, water, and fire, because those are all the basic things that we could see around us. Later on, it was discovered that there are much smaller elements, and those really aren't elements. I mean, earth is a mixture of elements. Water is H2O. It's a compound. Air is a mixture of compounds, like CO2, molecular oxygen, molecular nitrogen, and a couple other gases. And fire really is a plasma. It's not really an element. But later on, we discovered these structures called atoms, and atoms are the most basic units of what we call an element. And an element's a type of matter which can't be changed by normal chemical means. In the past, there was a field of inquiry called alchemy, and the idea was you could change lead into gold. And you can change lead into gold, but it requires things like stars to do it. It can't be done in regular chemical settings. So some examples of elements include gold, oxygen, copper, hydrogen, carbon, nitrogen, silver, lead, phosphorus, sulfur, einsteinium, which is a element that's produced in large particle colliders. And these are the ones that actually produce through artificial techniques. So the periodic table. If you look at your book, figure 2.2 in your book, there's a picture of a periodic table. And this arranges the elements according to categories. And if you notice, they're set up in columns. In each one of the columns, generally the elements have the same sort of the same sort of properties. So hydrogen and sodium, Na and H, are in the same column. They're very reactive elements. In the last column, all the way to the right, you have helium, neon, xenon, argon. These are called the noble gases, and they are very stable elements. They do not react with other things. Hydrogen, lithium do react to things. They're highly reactive. And hydrogen and helium are the two most abundant elements in the universe, with hydrogen representing around 90%, helium representing close to the other 10%, and lithium being relatively high in abundance as well. And all the other elements, such as oxygen, carbon, iron, gold, etc., are very small amounts throughout the universe. So in the picture above, the Hindenburg blimp was one of the first blimps ever constructed to use hydrogen gas back then to fill it up. It's because it's the lightest gas, and it's very reactive, and it blew up. It was a very devastating scene for people to see. And today we fill blimps up with helium because helium's not going to explode. It's interesting, helium was discovered on the sun before it was discovered on the earth, and helium is an extremely light gas, and because it doesn't react to things, it actually escapes Earth's gravity, and we're actually going to go into a helium shortage eventually. We're eventually going to run out of helium on the Earth. Hydrogen, on the other hand, is even lighter, but when it floats up, the oxygen, the O2 in the atmosphere, will react with it and form water, and oxygen will hold on to helium, hydrogen, sorry, in the atmosphere. Not allowed to escape it, but we do lose some. So which elements compose living structures? So about 25 elements make up the majority of living structures. These are what we call the bulk elements. And the four most abundant of those 25 are carbon, hydrogen, oxygen, and nitrogen. Okay. Hydrogen is the most abundant element in terms of its actual number. Oxygen is the element that makes up the most weight. Carbon is an essential element. We'll get into this a little later. They all four are essential, but carbon is an element essential for organic molecules in that it has four little posts, if you want to think about it, where it can bind to other elements. And with those four different posts, it can create these long chains of carbon atoms posted together and all sorts of other elements posted to the sides of it. And so you have something that's very simple, so like 4 carbons in a row. And depending upon what elements you have attached to it, it changes the molecules dramatically in terms of how they interact. So for something very simple, you have a lot of potential diversity. So those 4 elements make about 96%. Most of the other elements consist 20 others, include phosphorus, sodium, potassium, calcium. Phosphorus is a big one. Sodium and potassium are very big in terms of for chemical reactions of the nerves. And then you have what we call trace elements. Copper is what we call trace element. Iron is another trace element. These are elements that are needed very, very extremely small amounts, but you would not survive without them. So copper and penny are good examples of that. And these are used by enzymes and in other molecules. And although they are needed in small amounts, you don't want to overload your system. But they're very essential for, like, enzymes are the molecules which help power chemical reactions in our body. And without these small amounts of iron and copper in our bodies, the enzymes wouldn't function, which means the chemical reactions wouldn't function in our bodies. So the percentages don't necessarily mean that anything's more valuable than anything else within the living organism. So the atom itself, let's get into the atom. Atoms are the smallest units of an element and consist of 3 subatomic particles. Now, if you remember from the organization of life, we started with the atom. And I notice a lot of students, I'll ask the question, what is the single most simplest form of life on a test? And students will often hit atom. And I see where that comes from. It's the smallest component of the smallest structure building of life in the organization of life. But there's actually smaller components to that. But the cell is the single most smallest entity of life. The atom is an inanimate object. It can't be a form of life in its own right. Okay, But atoms are the smallest units, and today we're going to go into a little more detail what the atom is. It consists of 3 subatomic elements, or particles. Sorry, particles. Protons are positively charged, neutrons are neutrally charged, and these are found in the nucleus, or the center of the atom. Electrons are the 3rd subatomic particle, and they move around the nucleus, and these have a negative charge to it. Okay, and the picture here depicts it sort of like if you think about the orbit of the Earth around the Sun and things like that. This is not really the way that it works, but it represents the idea that electrons surround the protons and neutrons. Now, the protons being positively charged, neutrons being neutrally charged, electrons being negatively charged, the negative charge of the electrons, the positive charge of the protons attract one another. So you're probably asking, why does an electron fall into the protons? Well, electrons by themselves are not really points or particles. What they are is they are more like a cloud. There's no single point in which an electron exists. And when that cloud collapses too far in, the negativity of the electron pushes itself back out. So there's always this balance between the negativity of the electrons and the positivity of the protons pulling them in, and the negative electrons keeping themselves out. So even if there's one electron in an element, such as hydrogen consists of 1 proton and 1 electron. That electron itself, because it's not a single point, doesn't fall into that proton. Okay, it constantly repels itself out. So atoms are defined by their atomic number. Okay, and what I mean by defined is that defines the name of the atom. Okay, and the atomic number is the amount of protons found within the nucleus. So carbon, for example, is 6 protons, nitrogen is 7 protons, oxygen is 8 protons, hydrogen has 1, helium is 2, lithium is 3, etc. Okay? So your identity is defined by the amount of protons you have. Okay? But the characteristics of an element, the defining features of an element are characterized by the electrons. The electrons are on the outer portions of the atom, and so thus they are the parts which are interacting with the rest of the other elements and light, for example, for the most part. Okay, so like gold glitters. Gold is defined by the amount of protons inside of it, but gold glitters because of the electrons flowing around the nucleus. Okay, iron has that cold touch to itself based upon the electrons, even though the amount of protons define the element as iron. And the reason why I'm pointing this out is because students often get this confused. Okay, so atoms vary in structure. Okay, the amount of electrons in the atom may vary without changing the name of the atom. Okay, normally an atom has the same amount of electrons as protons. Okay, but sometimes certain elements can steal electrons from other elements. For example, chlorine can steal the outer electron of sodium. Sodium is 1 electron in its outer shell, and chlorine has 7. And the way it works is, well, we'll get into this a little later, but electrons like to pair up. They're like us. Most of us like to have someone in our life. We like to have a significant other. Who the significant other varies between us, who we find attractive and everything. But we like to be paired up. We like to have someone with us. Electrons are the same way. Electrons don't like to be alone. They like to pair up. So if you have an electron by itself, and you have another element that's an electron by itself, those electrons like to get together. And depending upon the nature of the two elements, one element will either steal the electron or they'll share electrons with each other. But this is essentially how it works. And it's because of this we have molecules. If all the elements were stable and didn't react, like helium, argon, xenon, the elements on the far right of the periodic chart, the universe would just consist of elements. That's all there would be. But because elements are unstable, because elements react with each other, they form molecules, which leads to bigger structures such as you and me and planets and things. Okay, so When electrons lose electrons, when atoms lose electrons from each other, they form what we call an ion. And the element which lost an electron becomes positively charged. The one that gains electron becomes negatively charged, and they'll form what we call an ionic bond. Table salt is an example of an ionic bond. Chlorine steals electron from sodium. Chlorine becomes positive, sodium becomes negative. They bind together. So the number of protons within the nucleus defines the element. We've already established that. So 1 proton in the nucleus means it's hydrogen. 8 protons in the nucleus means it's oxygen, etc. Okay, but there's another way that elements can vary, and that's the amount of neutrons found in the nucleus. So in the picture to the right there, you have hydrogen with 1 proton, and then you have deuterium. That's a type of hydrogen with 1 proton and 1 neutron. And you have tritium, which is 1 proton with 2 neutrons. And it's interesting, heavy water is generally a water that has one of the varieties of hydrogen in it, tritium or deuterium, which makes the hydrogen heavier, and it makes water heavier in the end. The majority of the mass of an atom is the protons and neutrons. Protons and neutrons are just about equal. Neutrons are a little more massive than protons. And the way it works is the mass of an element is based upon the amount of neutrons and protons in the nucleus. Electrons are so small they're not even considered in the mass of an element. Okay, so if I gave you a question on the test and said, like, you have an element of oxygen, there's 8 protons, 8 neutrons, and 8 electrons, what is atomic mass? You'd add up the amount of protons and neutrons, okay, and that would give you the mass of the element. Okay, so here's an interesting little tidbit of information that I want you to think about. This isn't going to be on the test or anything like that. It's just something which I find to be amazing. But an atom itself, the nucleus, which consists of protons and neutrons, represents 99.99% of all the mass of that element. Okay, the other 0.01% or 0.05% of the mass, the element is the electrons. Okay, but let's say you blew up the atom to the size you average at the movie theater. So next time you go to the movie theater, you think about this. If the walls of the theater were where the electrons were, okay, the nucleus would be one of those little pieces of dust you see floating around in the movie theater. Another way you can think about it, let's say you blew up the nucleus the size of a basketball here in the Chesapeake campus. The closest electron would be out in Richmond. So matter itself, there's lots of space between it, and when you look at your arm, it looks solid, but there's a lot of space in between those atoms, in between those electrons and protons. So matter is chiefly made of nothing, really, when it comes down to it. Okay? So an isotope, if you notice on the second column over there, third bullet down on the right side, an isotope is a variety of the particular element which is identified by the amount of neutrons in the nucleus. So you can have oxygen 16, that's oxygen with 8 protons, 8 neutrons. You can have oxygen 17, that's 8 protons, 9 neutrons. You have oxygen 18, that's 8 protons and 10 neutrons. All 3 of those oxygens have 8 electrons, okay? And they're all isotopes of one another. You have potassium 39, potassium 40, potassium 41 there, and if you notice, they have 20, 21, and 22 neutrons. So the amount of neutrons doesn't necessarily equal the amount of protons. But there's always an equal amount of protons to neutrons to protons or more. The atomic mass is the average mass of all the isotopes based off of the proportion of the isotopes. So atomic mass is the average. The mass number is the mass of that particular element at that particular time. So isotope stability. Some isotopes are stable. The three different types of oxygen, O16, O17, and O18, are very stable elements. And you can actually use this to determine past climates. If you look in the structures of organisms, or the structures of corals, for example, you can see the types of isotopes that are present in oxygen, and you can see the variety. Now, oxygen 17 and oxygen 18 are very rare. They represent a very small percentage of the overall oxygen atoms found. But if you have a slight increased amount of oxygen 18 atoms in a particular coral, that makes the composition of the body of it up, you can determine that the climate at that time was laid down was a little warmer. And that's because you have a lot more evaporation occurring. The water elements, or the water molecules that have oxygen 16 are more likely to evaporate off, leaving a slightly higher concentration of O18 in the environment which the corals are absorbing into themselves. If the climate's colder, then you have less evaporation occurring, and that amount of O18 is decreased in proportions to the O16. And with that, and what you can do is these corals, they leave layers beneath of themselves, and those layers, you can drill through a coral reef and you can pull it out and you can determine past climates based off of that, at least the temperatures. Now, you're not going to be able to say like January 15th, 40,000 years ago it was 78 degrees or something, but you can determine whether it was cold or whether it's colder or warmer in that particular time period. So some elements are unstable as isotopes. So carbon-14, so carbon's normally carbon-12, 6 protons, 6 neutrons. But you have carbon-14. And what's interesting is nitrogen generally has a mass number of 14, 7 protons, 7 neutrons. And carbon-14 is 6 protons, 8 neutrons. And what happens is in the upper atmosphere, there are extremely powerful electromagnetic waves that come out of space due to like stars exploding and all sorts of things happening. And when these rays hit nitrogen, they sometimes convert a proton into a neutron. And when that occurs, you go from being nitrogen, which nitrogen 14, 7 protons, 7 neutrons, to carbon 14, 6 protons, 8 neutrons. Now, that proton, which can convert a neutron, it doesn't want to stay a neutron. It wants to go back into being a proton. And I'm anthropomorphizing by saying it wants to, granted. But to me, it just makes it a little more fun to talk about it. So there's a predictable rate at which carbon-14 will convert back to nitrogen, at which that proton which became a neutron will convert back to being a proton. And every 5,360 years, half of the C14 produced 5,360 years ago will go back to being nitrogen. And then in another 5,360 years, half of what was left will go back to being nitrogen, etc., until you get to a point where all that carbon-14 converted back to nitrogen. Okay? And what happens is plants absorb CO2 out of the atmosphere. And there is a steady amount of C14 versus C12 in the atmosphere. And when a plant is living, it'll take that C14 and it'll use it. The same thing will take that carbon-12 into it. Okay? But when it dies, it stops respiring, it stops breathing, it stops photosynthesizing, it stops doing everything. It has a set amount of C14 in its body. And every 5,360 years, half of that C14 will convert to nitrogen. And what we can do is, you can take a sample of that tree, and you can analyze it, determine how much C14 is in it. And with that, you can determine the age that tree had died. There's some limitations with this. This dating only works up to about 50,000 years ago. It's what we call radiometric or radioisotopic dating is what it's called. So uses of radioactive isotopes. We use it in medical research. We use tracers. These are radioactive elements that we put into the arteries. they flow around the body, and when there's a blockage in the artery, we can see where that blockage occurred. Okay, we use MRIs and CAT scans and things of that nature. The type of radioactive elements they use are not dangerous. Radiometric dating. So we already talked about carbon-14 dating. But there's potassium to argon dating, which can be used for hundreds of millions of years. Uranium to thorium. There are many different types of this materials, and use different forms of dating for different types of lengths of periods of time. And then we use radioactive materials for cancer treatments. Also kills normal cells as well. It's not a fun treatment, but it has shown to work to some degree. We're still working on other forms of cancer therapy and cancer cures. And then there's bad forms of radioactive isotopes that cause damage to the body. The radioactive isotopes that come out of nuclear power plants, things of that nature, nuclear waste. Contrary to comic books and movies, if you fall into some nuclear waste, you're not going to mutate and have special powers. You're going to mutate and have cancers is what's going to happen. And if it's particularly bad, those cancers are going to be really accelerated and you're going to pass away, unfortunately. But it'd be neat if you could fall into a vat of nuclear waste and develop some form of superpowers. I think it'd be really cool, but it doesn't really work that way. So atoms link together through what we call chemical bonds. Okay, so a molecule is a structure which consists of two or more atoms bonded together. And the simplest molecule is a dihydrogen. That's two hydrogens bonded together. They share electrons with each other, and they both have one electron. Remember, I said electrons like to be paired up, so this gives them two electrons which flow around each other. Now, a compound is a type of molecule which consists of two or more elements, dihydrogen monoxide, or water, or H2O. A very common compound consists of two hydrogens bonded to an oxygen, so it consists of two different types of elements. Another simple element is a sugar molecule, C6H12O6, 6 carbons, 12 hydrogens, 6 oxygens. That's a sugar, that's a glucose or a fructose, and they consist of 3 different types of elements bonded together. So the electrons determine the bonding patterns. Electrons exhibit what we call orbitals. Okay? And electron orbitals exist in what we call energy levels, which determine where the elements are found. Okay? Or where the electrons are found. Several electrons exhibiting the same amount of energy are found in an energy shell. Electrons exist best in pairs, but they must fill all the spaces of these shells first before they start pairing up. So carbon has 4 unbound electrons in its outer shell. What you think well, why don't those 4 electrons bind up together to form pairs? But there are 4 shells that have to be filled before they can pair up. So because there are 4 of them, each one goes to one of those shells, and each one of those wants to bind with other things. So an atom's valence shells are its outermost electrons, and these electrons create the chemical reactions which lead to bonding. So the outer electrons are the ones which create the defining properties of the element. So we have hydrogen with its 1 electron and helium with its paired electrons. The 2 electrons are in the same shell. The first shell is isolated by itself, and the electrons will fill that up 1 then 2 before they go on to other shells themselves. Hydrogen being extremely reactive, helium not being reactive at all. So electronegativity. So this is where the nucleus plays a factor into it. Electronegativity is the amount of pull the protons have on the valence shell electrons. And it's based upon a scale. 0 means no strength, 4 being the strongest. Okay. So there are different types of bonds. One is called covalent bond. And this is where the atoms that are bonded together share similar strengths in electronegativity. and they share electrons with each other. And there are two types of covalent bonds. One is what we call a non-polar covalent bond, and this is where the electronegativity value differences are less than 0.5. So for example, carbon has electronegativity value of 2.5, hydrogen has electronegativity value of 2.1, the difference is 0.4. So they share the electrons equally with each other. So ethane, which is 2 carbons and 6 hydrogens bound together, form what we call a nonpolar covalent bond. What we mean by nonpolar is because the electrons are shared equally, there is no positivity or negativity in the element itself. Okay, so let's go to the next one. A polar covalent bond is when the value differences are between that of 0.5 to less than 1.9. So hydrogen has a value of 2.1, like we stated earlier. Oxygen, though, is a very strong element. It's a value of 3.5. So the difference is 1.4, which means the oxygen atoms tends to pull the electrons a little more towards it, and the hydrogens are left without electrons for the majority of the time. So the hydrogens are slightly positive, the oxygen is slightly negative. So it creates what we call polarity. Even though the electrons are shared between the oxygen and hydrogen, the oxygen is sort of that friend of yours growing up who used to borrow your toys more than lent you toys. And because of that, the oxygen is slightly negative and you're slightly positive because you're nicer. But on occasion, your friend gave you toys to play with. You lent you toys. On occasion, you didn't let your friend have toys. So on occasion, the hydrogens are negative and the oxygen's positive. But in general, the oxygen's negative and the hydrogens are positive. Okay, and this is going to lead to a whole bunch of things that are going to occur later on when we talk about water molecule as a whole. Okay, so nonpolar values of less than 0.5 and the differences. And the electrons are shared equally, so there's no negativity or positivity in the element. Polar covalent bonds, 0.5 to 1.9, and there's slight negativity on one side, slight positivity on the other side of the molecule itself. So what happens to get to even greater electronegativity value differences, say 1.9 or more, you form what we call an ionic bond. So chlorine has electronegativity value of 3.0, while sodium has electronegativity value of 0.9. The difference is 2.1. Chlorine is so strong that it rips the electron away from the sodium. And the chlorine will become negatively charged, sodium will become positively charged, and because they have this positivity negative charge, they bind together in the form of what we call table salt. Okay? So this is the other end. This is the nasty, ugly end of a bond, if you want to think about it that way, where one element steals the electron from the other one. This forms an extremely strong bond between the elements. Ionic bonds are the strongest. Covalent bonds are the next strongest bonds. Covalent bonds form more molecular structures. Ionic bonds, they do form molecular structures, but they're limited in their structural size and their structural complexity. So the last form of bonds we call hydrogen bond. Okay. And hydrogen bonds form between partial negative and positive charges due to polar covalent bonded molecules. So, and a classic example of that is water. So because water, the oxygen is slightly negative, the hydrogen is slightly positive, the negativity of one water molecule's oxygen will attract the positivity structure of the hydrogen of another water molecule. These form called hydrogen bonds. Hydrogen bonds are weak. They don't last that long, and they're easy to break up, but they're easy to reform too. And when we talk about water later on, the hydrogen bonds create a lot of the properties of water, which is, and water is a rather unique compound on the Earth, and it's something necessary for life as far as we know it. But hydrogen bonds are also part of, say, like our DNA. When we get later on in DNA, DNA forms two strands together, they twist together. But it's hydrogen bonds which hold those two strands together. We'll get a little later in the second of these videos. Okay. But so water itself, essential to life. Water makes up roughly around 62% of the human body. That's a little slightly less in women than men. Women generally have a little more fat tissue in their bodies, and that's to insulate against for a developing embryo and fetus. Men, on the other hand, don't have to worry about a developing embryo or fetus in their body, so we have slightly less fat but more water. So astrobiology is a search for extraterrestrial life. One of the things that astrobiologists are looking for is water, liquid water on planets. If they find liquid water on planets, the keyword is may. They may have a planet which could have life on it. Now, could there be life without water? It's possible, but we don't know. But we do know that life here exists. Anywhere you have liquid water, life exists on the Earth. So we're pretty confident that we find the planet with water. There's a chance that life could be on it. So Europa is a moon of Jupiter. It's really neat. It's frozen on its surface, and it's frozen ice, but it probably has liquid water in its core, and there's pretty defining evidence for that. And one of the things is that the ice structure itself shifts and changes. And as this moon of Jupiter goes around Jupiter, Jupiter is such a massive planet that it creates friction within the center of Europa due to gravity. And this friction warms it up, which makes liquid water in sort of the internal portion of Europa's ice. And there's a thought process there could be life inside of it, but it's impossible to tell. Mars is another planet with frozen water, and it had liquid water on its surface. We're pretty sure of that with all the evidence that we're finding. And not only that, but we're discovering evidence of liquid water on Mars in the present, although it's very transient. Mars generally is below freezing, but on occasion it gets above freezing. And there's evidence of water, liquid water melting on Mars. And but in the past, Mars probably had a different atmosphere to it as well. And I could talk about it, but it would require a whole length of time that I'm unwilling to devote right now to it. If you would like to know more about the atmosphere, the previous atmosphere of Mars, email me, and I'd be more than welcome to discuss it. But water is found throughout the universe. It's found everywhere. It's one of the simplest compounds. Oxygen is one of the more abundant elements in the universe. Hydrogen, helium, and lithium obviously are the most abundant, but oxygen is pretty high up there as well in comparison to the other elements. So water is cohesive and adhesive. So the polarity of water and the hydrogen bonds leads to water's property of cohesion. It allows water to hold on to each other. Okay, water will form bubble shapes over the rim of a glass. If you ever noticed that, water form beads because water is cohesive, because water bonds to each other through hydrogen bonds. Okay. Also, the ability to hold surface tension. So here, there's that glass of water, and the reason why it doesn't spill over, even though you went a little over the edge there, is because the water bonds are holding on to each other. Okay. Water has the ability to keep its surface tension up. And water striders are these little bugs that can crawl around on the surface of water. Okay, and they can do that because water has a certain amount of strength to it. So the polarity of water leads to the properties of adhesion, which is the ability of water to maintain its surface. Water goes up trees, and the reason why water goes up trees is because at the leaves there are these structures called stomata. We'll get into these a little later on semester and talk about photosynthesis. But stomata are the result of two cells called guard cells, and they open up. And when they open up, they allow the plant to be able to breathe. Now, when they breathe, water evaporates out of it. And when that water molecule evaporates out of it, it tugs on the water molecule next to it, which tugs on the water molecule next to it, which tugs on the water molecule next to it, etc., 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 all the way down the roots. And as the water evaporates out of the leaf, it pulls in the water next to it, which pulls water up the plant. So plants don't have to use any energy to pull water up. They just do it through cohesion. The meniscus of water forms in a graduated cylinder. If you ever notice in a graduated cylinder, look at it. Next time you use one in the lab, And you'll notice that there's this curvature of the water. That's because the water is binding to the glass on the side, and it doesn't just flatten out. Hey, water dissolves many other substances. Water is known as the universal solvent. It'll dissolve most polar substances, which includes polar covalent structures and ionic bonded structures. So sugar, for example, will dissolve in water. Ionically bonded salt will dissolve in water. Okay, these are what we call hydrophilic substances. Hydrophobic substances, think of water-fearing fats, oils, and waxes, do not dissolve in waters because they are non-polar covalent bond structures. So polar covalent bond structures and ionically bonded structures will dissolve in water, but non-polar covalent bond structures won't. So the oceans are saltwater because they've been around for billions of years. They've been eroding at the bottom of the ocean, and they've been eroding salts out of the water. Lakes are freshwater because they've only been around for a shorter period of time. The Great Lakes have only been around for like 10,000 years. After the last ice age, there were big glaciers on there, and they melted, and ice is fresh water. And this water that persists today is fresh, and they've only been around for 10,000 years, so they've been only eroding at their basins for a very short period of time. The Pacific Ocean, Atlantic Ocean are all part of the oceanic system that's been around for billions of years. So, and this is an important thing for you to understand for lab as well as lecture, but a solution is a liquid substance which has a solvent. Water is the universal solvent, and one or more solutes. Those are substances which are dissolved in a solution. So a typical example of a solute is salt you add to a soup. The water is the base of your soup, and the salt you add to it dissolves in it, and it adds flavor to it, obviously. Okay, so a solution is a liquid which has a solvent, water, and one or more solutes in it. So water and temperature. Water moderates temperature throughout the globe. It takes a lot of energy to change the state of water. And that's the interesting thing about water. Think about the majority. The majority of things you know of are either in solid, liquid, or gas form. But water is one of those few compounds or molecules that can be found in frozen ice, liquid water, or in a gaseous state. Okay? That's because we have a range of temperatures here on the Earth that accommodate all those three states of the water molecule. Okay? Well, it takes a lot of energy to convert, say, a liquid water to an evaporated form of water. That's the reason why we sweat. We sweat so that we put water in our body. It takes energy for that water to evaporate off. When that water evaporates off, then it cools us down. Okay? Oceans itself. Have you ever gone swimming in May by the beach? It's cold, even though the air temperature may be warm. It may be 70s, 80s, sometimes 90s in May. And you go and you're like, oh my God, it's a nice day. I'll go to the beach. And you go to the beach, you jump in the water, like, whoa, it's cold. It's because it takes a long time for the heat of the sun to warm up the water. But sometimes you've ever gone swimming in September, sometimes even October, and the waters are still warm, but yet the air temperatures have cooled off. So the atmosphere's temperatures can vary considerably, but the water temperatures will stay stable, and they'll tend to fluctuate. And that's one of the reasons why, say, like the Virginia Beach area generally is warmer in the winter than, say, Richmond. Richmond's far away from the water, and because the water, even though it does get cold in the winter, it doesn't get as cold as the atmosphere does. So it buffers the temperatures out to some degree. I'm not saying it doesn't get cold in Virginia Beach. It does get cold in Virginia Beach, but it doesn't get as cold as often. Ireland, for example, Ireland's up there in the same sort of area that Nova Scotia is in terms of its northerly placement on the Earth. But it's warmer than Nova Scotia, and that's because the Gulf Stream carries warm water up from the equator up to Ireland and warms it up. Now, Ireland's not as warm as it is in the Caribbean, or in the equator, but it's much warmer than, say, Nova Scotia is during the winter. It doesn't get nearly as much snow as Nova Scotia does. And the interesting thing is water expands as it freezes and forms solid. Now, most things, when they go from gaseous to liquid to solid, they get more dense. But water is one of those strange elements that it's most dense when it's still a liquid. It's 4 degrees Celsius. It's still dense, and water freezes at 0 degrees Celsius. And the reason for that is because when it freezes, it actually crystallizes, and the water molecules actually move out from each other a little bit and make the water molecule less dense. So ice floats, even though it's a solid, because it's less dense than the water around it. So this allows for things like ice fishing. I've never done it before, but I imagine it's kind of fun. I'm not sure, but I don't know. The walrus looks happy, but walruses are better adapted for sitting on ice than we are. So water is a key component for chemical reactions. Chemical reactions are 2 or more molecules exchange 1 or more atoms and yield different molecules. So for example, here we have methane and oxygen, and they form CO2 and water. This is a simple reaction that occurs, and water essentially allows these things to occur to some degree. The CH4 and the 2 oxygens are the reactants of the chemical reactions. Think of the ingredients to a cake you may make. So you take the ingredients, and from that you produce a cake in the end. The CO2 and water are the products. And so you need the ingredients, and then you have your products. So on the left side of the equation, on the first bullet, or the sub-bullet of it, CH4 plus 2O2. So let's go over this. So what the CH4 means, so C stands for 1 carbon, H4 represents 4 hydrogen atoms, and that's all part of the same molecule. So this is a molecule that consists of carbon and 4 hydrogens. So the other molecule there, 2O2, the big 2 there is signifying there are 2 of these molecules, and each of the molecules consists of 2 oxygens combined together. So whenever you see a big number beside the first part of a molecule, that's telling you the amount. And we could put 1 CH4, but there's no real reason to put the 1 there, so we don't do it. And then on the other side there, you have CO2 plus H2O. So you have 1 carbon dioxide, it's carbon with 2 oxygens, and 1 water molecule. And I actually just realized the mistake in that, so let's correct that mistake. Okay? So there'd be 2 water molecules there. Oops. I want to get rid of the hydrogen. That'd be rather crazy. There we go. So you have your reactants to the left and your product to the right. So acid and bases. An acid is a substance which adds hydrogen ions to substances. So hydrochloric acid and sulfuric acid are 2 examples, very corrosive. Vinegar and lemons are acidic. If you have foods that are slightly acidic, they're generally sour in taste. Not always, but they're generally sour. I'm thinking lemons. A lot of your citrus fruits are that way. Bases are substances which have OH ions, and they tend to accept hydrogen ions that are in the substance. If you notice, take the H plus and OH, they form water. Okay, and that's what will happen if you take an acid and a base that are equally strong and mix them together. They will form water in the end. So bases are typically bitter tasting, and a lot of bases are poisonous. It's one of the reasons why we generally don't like bitter tasting things, but we sometimes like sour tasting things. I'm not suggesting you eat everything that's sour, and not eat anything that's bitter, but in general, these are the way things are worked. So a neutral substance is one that has the same amount of hydrogen ions and OH ions and results in water. Living organisms maintain their internal constancy, and this is one of those things that we're maintaining in our internal environment, is we're maintaining our pH levels. So pH is the measure of acidity or alkalinity, which is the base of a substance. Alkalinity is the fancy way of saying base. So, and it's based on a scale of 0 to 14. 0 to less than 7 is acidic. Okay, more than 7 to 14 is an alkaline or base. and a pH of 7 is neutral. Okay, so every unit that you go down the scale, you are either increasing acidity by 10 times or decreasing alkalinity by 10 times. So you say like you have a substance that has a pH of 14, you go to pH of 13. You've decreased the amount of alkalinity in the substance 10 times. If you went 14 to 12, that'd be 100 times. 14 to 11, 1,000 times. If you had something at acidity of 7 and went to acidity of 5, that means you went to 100 times more acidity. You went 7 to 6, that's 10 times. 6 to 5, that's 10 times. 10 times 10 is 100. And here's your basic scale. So you have 7 neutral, that's your water. 9 is baking soda. Okay. Bananas typically have 5. Tomatoes have 4. Lemons have 2. Your stomach has a pH of 2. Okay. Vinegar has a pH of 3. So this is a good chart representing the various substances and what their pHs are and such. If your pH, your stomach gets too low, if you eat a lot of acidic foods and it gets too low, you'll develop heartburn. So organisms maintain their pH by diet and by releasing buffers. And buffers are substances which can bring the pH back to its normal scale. And then we have Tums and things like that you can take even if your buffers aren't working all that well. So other things, if you eat too much tomato sauce, you have too much spaghetti, too much lasagna, you can take a Tums, and it will or Pepto-Bismol and other things which will bring your pH back into its normal balance. Okay, so let's stop here right now, and I'll get into organic molecules with the next video. I hope you found this to be informative and helpful.